Ahmet, go for it.
Hello, everyone. Thank you for being here. The last speaker of the day is Montaha from Bahçeşehir University. Today, she is going to give us a talk about Toric varieties. Good luck, Montaha.
Hi everyone, I'm Montaha Naouar. So first I'm going to give the topological definition of what Toric varieties is, and then use an example. I'm going to connect the first definition and then I'm going to give a new definition and construction of Toric varieties using codes. Okay, so let's first start with what a torus is. A torus is an affine variety, isomorphic to C star and grouped under component Y. An affine variety is just a set of zero locus of finitely many functions. So basically the point where the function. A fine Toric variety is an irreducible affine variety V, such that there's a torus inside of V and isomorphic to C star n. And also the action of T on T extends to the action of T over V. So which actually means that multiply everything by zero, it actually gives zero. Example of a Toric variety is Cn and C star n with the torus B and C star n. Character of a torus is a morphism chi from T to C star. Homomorphism. Example, if we have m and Zn from A1 to An, then the character m chi m from C star n to C star that takes the point T1 to Tn to the product of T1 to the power of A1 until Tn to the power of An. Okay. Now we know that all characters of C star n, they form a group isomorphic to Zn, and characters of a torus T is form a lattice M of rank equals to the dimension of T, which means then which implies that chi M is from T to C star. What a lattice is just a free abelian of finite rank isomorphic. And we know that T a torus and H is subvariety irreducible inside of T implies that H is also a torus. And if we have a function that takes you from T1 to T2, both torus, and that function is a morphism, then the image of T1 is also a torus. Okay, a one parameter subgroup of a torus T is a morphism from C star to T, that is also a group on T. For example, in Tn, T1 to Bn gives a one parameter subgroup sigma U from C star to C star n that takes you from T to the point T to the power of T1. The group of one parameter subgroups of C star n is also isomorphic to Tn, and the one parameter subgroups of a torus T also form an abelian group lattice n of rank equals the dimension of T. Now we're going to see the bilinear pairing, which is the inner product. Okay, so from M to F. From M cross N to Z, that takes you from I M composition lambda U to L, would be in the composition from C star to C star that takes T L for some time. We have a torus T is star N, like goes to be C star N with M. Then the inner product Mn is equal to the product of Ai's Ti's. You can see that by just doing the composition. This by lambda U is equal to.
Can you please speak?
Chi M is circle lambda U. So chi M of the image of lambda U, which is T to B1 to T to Bn, is equal to the product of A1 B1 to Vn, which is T to the whole product AI Bi. Okay, now we're going to see the examples that takes us from the first definition to the actual forms. Let's consider the variety B, XY minus DW and C4 or C star 3. We have the map that takes you from T1, T2, T3 to T1, T3. We have an M and an M, ABC, which is isomorphic. Then we get the function psi M on V, defined by xi, y, xa, yb, zc. If all of them are positive, then it extends as every point is well defined, the function is continuous, everything is good, so it extends. But if we have that C is negative and A plus B and B plus C are positive, then we can see as xy equals zw on V, then xy, xa, b, yb, zc is equal to that one right here. And as minus C here is positive, and here is positive, and A plus B is also positive, then we have a well-defined function, continuous, and everything is good. So we get an extent from B. And this takes us to the inequality A positive, B positive, A plus B is positive, B plus C is positive, which defines the corresponding cone corresponding to B. An image of the cone, the lattice containing the lattice points corresponding to our variety that we're talking about. Okay, so a complex polyhedral cone in a vector space NR is sigma is equal to cone of S, which is the sum of lambda u with lambda u being positive and R. Example, we have the first quadrant of R2 is a cone. The cone E1 minus generated by E1 minus E1, which is a line in R2, is a cone. And the cone generated by E1, E2, E1 plus E3, E2 plus E3, R3 is also a cone, which is so for these cones, we have a polyhedral cone, then we can find the dual cone by having the set of M and N with the inner product of M and N being positive for every U in the cone. So yeah, MR here is the dual lattice of NR, both isomorphic to Rn, and Mn is just the natural pairing between M and N. If we have a rational polyhedral cone sigma, yes, then sigma is equal to cone of S for a finite set S. For example, we have this cone right here, which is the plane generated by E1, E2, and we have the dual cone here, which we got by having every vector orthogonal or perpendicular to the plane. So that's our dual cone. We have another example gotten by the same way, cone generated by E1 plus E2, are this cone and dual cone, the same thing. Now, if we have a rational polyhedron cone, then we can define S sigma semigroup, which is the intersection between the dual cone and which takes us to the Gordon's lemma. If we have a rational polyhedral cone, then S sigma is finitely generated. Now, if it's finitely generated, then we can see that C of S lies in the ring of Laurent polynomials, and therefore we can define what defined Toric varieties is again. So finally, sigma is a strongly convex polyhedral cone. Then you can have a Toric variety, which is equal to the spectrum of C as sigma, the intersection of lambda V and M. That's the affine Toric variety associated. An example, same one. If we take a cone from E1 to ER and Rn, with B and R between 0 and N, and we get the dual cone, which is of this form right here. then you can get the correspondent Toric varieties, which is the spectrum of this one right here. And if you get, for example, R is equal to 2 and N is equal to 3, then we have our example, the one that we listed